Hello everyone. In today's talk, we are going to take you through a hot topic in the compute world, AI acceleration on chip. We are going to show you how to exploit matrix math assist architecture, in short known as MMA, for AI acceleration on Power 10 microprocessor. My colleague Puneeth Bhat and I will take you through the following topics. First, I will cover the basics of my MMA architecture. We'll discuss details on the register handling, supported data types, and the compute instructions supported by MMA. I'll also introduce you to the recently announced IBM Power 10 microprocessor and will discuss its MMA compute and bandwidth capabilities. Puneeth will cover the basics of MMA programming using GCC built-ins. We'll take you through a simple MMA programming example and we'll touch base on OpenBLAS support. He will conclude the talk with the overall performance uplifts achieved in Power 10 for AI workloads. MMA architecture support is introduced in Power ISA version 3.1. This introduces a new set of instructions along with required architecture enhancements in register handling to support dense matrix math operations. Dense numerical linear algebra computations are the core of the emerging AI machine learning and deep learning workloads. This MMA architecture will cater to the needs to fulfill the huge compute demands presented by the MLDL workloads. There is a wide scope for innovation to apply these fundamental math operations supported in MMA for other computations like fast Fourier Transform, arbitrary precision arithmetic, etc. Moving on to the next slide. Power ISA has support for 64 vector scalar registers to fulfill all the compute requirements of the VSX instruction set. As part of MMA architecture, 8 registers, each of size 512-bit, called accumulators, are introduced. These are software-managed shadow to a set of 4 consecutive VSRs. As shown in the figure, 32 VSRs 0 to 31 are mapped to 8 accumulator registers 0 to 7. Users must choose to either use the register as VSRs or accumulators. It cannot be used both ways. State must be explicitly transferred between the VSRs and the accumulators. In order to load the data into the accumulator, users should first load the values into the VSRs. Once the data is loaded to VSR, the state can be transferred to accumulator using VSX move to accumulate instruction. After the computation is done, the values can be brought back from accumulator to VSRs using the VSX move from accumulator instruction. Once the data is available in VSR, other instructions can operate on this data. Moving on to the next slide. MMA architecture supports math operations on 4 different floating point data types: FP64, FP32, FP16, and bfloat16. In addition, it also supports 3 integer data types: int16, int8, and int4. These diverse set of precision levels and data type support is provided to cater to the needs of on-chip AI inference acceleration. Equivalent compute instructions are supported to handle each of the above-mentioned data types. Each of the MMA instruction takes 228-bit input values and it generates a single 512-bit output value which can get accumulated to the respective accumulators. This is explained in more detail in the next slide. To highlight the capability of the architecture, a single FP32 MMA instruction can perform 16 multiply add operations in one go. FP16 and int16 MMA instruction can perform 32 multiply add operations. Int8 can perform 64. Int4 can perform 128 multiply add operations using a single instruction. The outer product MMA instruction can be read using the format mentioned in the slide. Type and rank determines what data type you are operating on and the respective rank for the operation. MMA instruction also supports lane masking feature, where it provides capability to reduce the number of multiply add by masking certain input values and produce less than 512-bit output. Moving on to the next slide. This slide gives you two examples of how MMA instructions operate. The first picture shows how a FP32-bit MMA instruction will operate. This instruction takes 228-bit values as inputs. Input 1 has 4 32-bit values. Input 2 has 4 32-bit values. Each of this 32-bit value will get multiplied with each of the other 32-bit value to generate 16 32-bit outputs. This, in turn, will get accumulated into the accumulator register. We can loop on this operation till the entire math function is complete. The second diagram is a representation of an int8 MMA instruction. Input 1 has 16 8-bit values. Input 2 has 16 8-bit values. Please note that here the first 4 8-bit values of input 1 gets multiplied with the respective 4 8-bit values of input 2, and these 4 output results will get summed up to get a 32-bit output. Overall, 16 such 32-bit outputs will get generated as part of this whole operation to generate a 512-bit output, which in turn will get accumulated to an accumulator. In total, 64 multiply-add operations will be performed. Moving on to the next slide. IBM recently announced its Power 10 microprocessor, which is fully compliant with Power ISA version 3.1. Power 10 processor can support up to 30 SMT8 cores or 60 SMT4 cores in a single socket DCM module. The diagram in the top left shows a picture of a Power 10 SMT8 core. This core can be partitioned into 2 SMT4 cores. Each SMT8 core can support 4 MMA instructions in a single cycle. In terms of flops capability, for double precision, it can support 64 flops per cycle, and it goes all the way up to 1024 operations per cycle for INT4 data type. Apart from the MMA unit, Power 10 also has capability to perform 8 regular SIMD operations per SMT8 core to support regular SIMD operations through VSX instructions. In comparison to Power 9, Power 10 has 2 times the regular SIMD capability and a brand new 4 512-bit matrix math acceleration engine per SMT8 core, which can generate 2048 bits of output every cycle. These huge compute capabilities will help accelerate AI-infused workflows in the enterprise market. Now that we have seen the compute capabilities, it is very important to feed these MMA and SIMD engines. In order to support the data demand to feed these huge compute engines, the data bandwidth has been doubled, starting from the OMA interface all the way up to L1 cache. Features like Fusion, 32-bit load instruction support aids these data demands for the MMA unit. Overall, each SMT8 core can support 4 32-byte loads and 2 32-byte stores every cycle from L1 cache. With this, I will hand it over to my colleague Puneeth to cover the rest of the agenda. Over to you, Puneeth.
Thank you, Satish. Hello, everyone. I am Puneeth Bhat. From here on, I will introduce few programming aspects of MMA in the following section and conclude the talk with few performance numbers. So, programming these MMA in-core accelerators have been made easy by the compiler built-ins provided by the latest GNU-C compilers. These extensions can be enabled in GCC by providing Power 10 CPU flag. As described in the table, there are various built-in types to support all functionalities and instructions of MMA. New data type of vector quad can be used to specify an accumulator, and a normal VSX variable can be specified using vector data types. There are APIs to assemble or disassemble the accumulators to be used as pairs or independent VSX registers. One can also make use of move from or to instructions to move data across VSX registers and accumulators. All sets of GER instructions, that is matrix multiply instructions, are covered to perform just multiply or multiply accumulate or multiply negate and accumulate with various suffixes. These combinations are useful in computing complex and real-time data types. The prefixed or masked instructions are also supported by the compiler built-ins, wherein masks can be specified as unsigned info flags. These prefixed or masked instructions can be used for partial operations in boundary conditions of a matrix multiplication where the sizes are not multiples of 4. Twin register pairing unpairing APIs are also available to be used with double precision GER instructions. These instructions are little different unlike others, as it takes a pair of VSX registers for first matrix and one VSX register for the second matrix, resulting in a 4x2 smaller resultant submatrix. The full list of all available built-ins can be found in the links specified. Moving on. In this section, we present a simple C example of a single precision matrix multiplication using vector outer product using GSA built-ins to accelerate on MMA. The accumulator ACC underscore T defined in the code section is defined as a vector quad type and initially is set to 0 using the built-in API. The same can also be achieved in optimized kernels by preloading partial result sums to VSX registers and moving data across accumulators using move to instructions. The compute kernel loops over the transposed first matrix and B matrix over K rows in strides of M and N to compute one 4x4 resultant submatrix. Finally, the accumulators are disassembled and stored back to the resultant matrix in strides of 4. To compute the full resultant matrix, it is required to loop over whole of M columns of the transposed matrix A and N columns of matrix B in strides of 4. So the same kernel can be called M by 4 into N by 4 times to generate full resultant matrix, which is not shown but assumed here. At the right hand side, we present with a detailed diagram an advanced and optimized SGM kernel generation procedure. Here, the same 4x4 example is optimized using 8 accumulators and reusing the same loaded A and B matrix values to generate a bigger 8x16 resultant submatrix. This results in 2 plus 4, which is 6 loads and 8 compute instructions with a better optimized and faster gem kernel. Moving on to the next slide. This section describes mixed and lower precision support in MMA. To perform a mixed or lower precision matrix multiplication operation using MMA, the input matrices needs to be transformed. Since the result matrix for any lower precision matrix math is still 32-bit, one accumulator can still hold a 4x4 resultant submatrix. To achieve the same and as described previously, ISA performs internal multiply accumulations within a subset and then accumulates the partial result to a bigger set. A simple transformation for an int8 matrix multiplication is explained in the figure at the right hand side. Similar transformation operations can be performed for int4, which extends and include 8 elements within a subset, and for int16 and half precision, this gets reduced to 2 elements in a subset. Moving on to the next slide, where we discuss on the community adoption of MMA. For community adoption, MMA support has been enabled in the latest OpenBLAS library. OpenBLAS should be built with Power 10 as core and libcore to enable MMA kernels for L3 BLAS routines. Currently, support is available for float, double, complex, and real-type GEM and TRMM kernels, which are triangular matrix multiplication. Using this OpenBLAS support, libraries like NumPy and frameworks like PyTorch can make use of MMA in-core accelerator readily to optimize real-time machine learning applications and deep learning inference workloads. Easy integration can be possible with any library or framework which can link to OpenBLAS for BLAS routines. Most common HPC and AI applications, which include compute patterns of GEM, convolution, clustering algorithms, variants of fast Fourier transform using vector outer product, etc., can get benefited by MMA in-core accelerators. Finally, looking on the performance aspect, as per our pre-silicon based lab experiments and performance assessments, Power 10 systems with MMA show significant improvements in compute and hence improved AI applications. OpenBLAS SGEM shows more than 4x per core performance improvements on an average for multiple matrix sizes compared to P9. Traditional LinPack and FP32 ResNet 50 inference workloads shows around 10x improvements. Lower precision ResNet 50 inference workloads shows up to 20x improvements as compared to P9 systems. With that, we conclude our today's presentation on Matrix Math Assist for AI acceleration on Power 10. Thank you for listening.
Okay, I see a few questions popping in the Q&A section. So let me try to answer some of those. So one question from Mandy is, in theory, no code changes required, assuming you compile your frameworks using OpenBLAS. Yes, I think you're right. We have the optimized kernel integrated as part of the OpenBLAS. Our OpenBLAS library team did a tremendous job in getting that done quickly. So we can just take the frameworks, just link it to the optimized OpenBLAS, and you should have your framework running as long as the framework supports that particular OpenBLAS version of library. So that's the answer for that question. Yeah, so one of the, so the other question from, I think, Mandy, are the optimized frameworks which are part of OpenBLAS listed somewhere? Okay, so one example is PyTorch. Puneeth, you want to take that question?
Yeah, sure. So currently, as we mentioned, it's been enabled for those four gem routines, the SGEM, the double precision, complex, and real. So those are the kernels which currently use MMA instructions as part of both the matrix multiplication and DRMM kernels. So you can look at these kernels within the OpenBLAS, but I'm not sure if any documentation exists as such on the list of these anywhere in OpenBLAS.
Okay, the next question comes from Vipin. Can you share the number of instructions and cycle count for performing the MMA instruction? So if I understand right, are you asking about, if you are asking about the number of loads to the number of MMA instructions? Yes, we do have the numbers in terms of cycle count. It depends. I'm not, okay, yes. So it's 6 loads for 8 MMA compute instructions, right? Puneet, that's the number we have, right?
I mean, I'm not sure if I understood the question correctly, but if it is like how many instructions are required to perform one 4 cross 4 matrix multiplication, then it is just one as explained from the ISA. But if it is like how much is required for an M cross and matrix multiplication, I think it depends on how optimized kernel you write. And as per the optimized kernel which was shown, which can compute at most 8 cross 16 matrix sub matrix at a time. So for that we need 8 loads versus 6 loads versus 8 compute instructions to generate one 8 cross 16 matrix.
Right, and Power 10 supports at SMT 4 core level. It supports 2 MMA instructions as described in the slide. So effectively, you can do every cycle 2 MMA instructions, and OpenBLAS, if you're like having the right input data set, right, you will see the max utilization of the MMA unit to large extent, right? It will be there are certainly some support instructions that has to come in for prefix or prolog kind of cases. So over that, I think MMA utilization is every cycle you can do 2, and that way I think you can achieve the best numbers there. What about the next question comes from Florin. What about ESSL support? Yes, so ESSL will be supported for MMA. So that will be officially released in some time, right? So the OpenBLAS is ready now. So we'll have to work through some of the ESSL aspects, and it will be at least it will be ready by the time we have the P10 systems launched. Okay, the other question comes from Jay. TensorFlow, of course, uses Eigen, no OpenBLAS. How's the MMA-enabled work in Eigen going? Yes, I think Eigen support is in plan, and we will have the support for Eigen as well. Yeah, so it will be certainly supported. TensorFlow, you can run it with MMA-enabled core as part of Eigen support. Yeah. So again, another question from Jay. Which version of GCC is the -NCPU Power 10 option enabled in?
Yeah, it's been out in the community in the dev version. The next release would have that enabled. For now, you can just build the GCC which is in the dev version.
Okay, I think those are the questions. Vipin, I hope we answered your question as well. Yeah, in case if you have any further questions, please drop us an email and we'd be happy to respond to you. Okay, so there is one more question coming in from, yeah, I think that's, Will is answering. Okay, it's GCC 10.2 has the MMA support.
Thanks, Bill.
Thanks, Bill.